Swayam Prabha. Digital India. Educated India.
Welcome again. Welcome to Basics of Noise and its Measurement. In this continuing series, at least for this week, we are exploring how the 1D wave equation is derived, its formulation, and what we are going to actually do today is combine all the three equations which we have developed over last three sessions: the wave equation, the continuity equation, the momentum equation, the continuity equation, and the gas law, and synthesize them into one single wave equation. And this is the equation which governs the propagation of wave in a fluid media which is elastic in nature and also which is inviscid in nature. It is important to understand that in this particular equation, the wave equation, we assume that the fluid is not viscous, and as a consequence, because of viscous effects, no heat is generated and lost in the process. So that is what we are going to do. We are going to develop the 1D wave equation for pressure. We are also going to develop 1D wave equation for velocity. And once we have done that, then we will also look at we are not exactly going to develop other equations, but we will definitely look at two other forms of wave equations. One is the wave equation in 3D Cartesian frame. So the 1D wave equation only governs this propagation of sound in one particular direction. Suppose you have a long tube with a uniform cross section and sound is traveling along the length of the tube. So this type of sound propagation is governed or dictated by 1D wave equation for Cartesian frames. So we will look at that, we will develop that, then we will also expand it into 3D wave equation for Cartesian reference frames, and then we will also look at a special form of wave equation for spherical systems where you have a point source, it's emitting sound, and that sound is spreading out radially in all the directions uniformly. So that is another form of wave equation which we will look at and comment upon. Okay, so very quickly I will recap the three different equations which we had developed earlier. So the first one was the momentum equation, and that is partial of pressure with respect to x equals minus rho naught partial of velocity with respect to time. So let's number this as equation A, and this is my momentum equation. Okay. The second equation which we had developed was the 1D continuity equation, and that equation is partial of u with respect to x times Vt equals t tau over dt, and we are going to number it as equation B. This is the equation for continuity. And the final equation which we had developed was for gas law, adiabatic gas law, and this is partial of P with respect to T equals minus gamma P naught over Vt times d tau over dt. This is equation C, and this is my gas law for adiabatic process. Okay, so that's equation number C. So what we are going to do is we are going to eliminate our aim is to eliminate u, our aim is to eliminate t from these three equations and ultimately come with one single relationship for pressure. So, when we inspect these two equations, what we see is that we have this term d tau over dt and d tau over dt in equations B and C. So, I can eliminate d tau over dt from these two, and what I get is, so from B and C we get del P over del T equals minus gamma P naught Vt, and instead of d tau over dt, I can get del u over del x times Vt. Okay, and this thing cancels out. So, what I end up getting is del P over del T equals minus gamma P naught. I can put this in parenthesis times del u over del x. So, let us call this equation T. Okay. So, the next thing we do is we compare equation D with equation A, and what we see here, and if our aim is to eliminate u, what we see here is that u has been differentiated with respect to time, and here it has been differentiated with respect to x, partially differentiated with respect to x. So, if I have to eliminate u, then what I can do is I can differentiate the whole of equation A with respect to x. So, then I will get a term del u, excuse me, partial of u, second derivative of u with respect to x and t, and I will also get a very similar term here in equation D. So, that is what I will do. So, if I differentiate A with respect to x, so from A what I get is, so I am differentiating the whole equation A with respect to x. So, I get partial of P second derivative with respect to x is equal to minus rho naught del over del x so this is my equation E. And similarly, I am going to differentiate equation D with respect to time. So, from D we get partial of pressure, second derivative of pressure with respect to time equals minus gamma P naught del of with respect to T times del u over del T. This is equation F. Now, we look at this term and we look at this term, and here we assume oh, I think I made an error here, it should be del x. So, here we assume that this cross derivative of u, where I am first differentiating time and then with respect to x, is same as this cross derivative and this assumption would be valid if my u is continuous in the whole field and also its derivatives both with respect to time and in space they are continuous. Not only the first derivative, but also subsequent derivatives, they are continuous in time and space across the whole field, then this assumption will be valid. If they are not continuous, then we cannot necessarily say that this assumption is valid. For instance, if you have a branching of flow, so in that kind of a situation, this assumption cannot be held true. So anyway, because those kind of situations are not here, so I take these things to be the same, and then what I can do is I can now eliminate these two terms from the equation. So what we get is from E and F, essentially what I get is second derivative P with respect to x is equal to minus rho naught, and instead of this cross derivative I get 1 over gamma P naught times del 2P over del T square. Okay. So what this gives me is this final equation, where C equals okay. So this is the wave equation. This is the 1D wave equation, and the value of C is this, and it just happens if you plug in the values for air, for ambient pressure, density of air, and the value of gamma for air, you find that the value of C, it comes out to be 344.2 meters per second. So this is the calculated value of C. At this stage, we are not saying that this C is same as velocity of sound. But if I actually measure the velocity of sound, then so velocity of sound measured, that turns out to be, for the same ambient conditions, 344.8 meters per second. So it looks like that the value of C is pretty close to the velocity of sound. And later we will see as to why the velocity of C, the value of C or the C is nothing but actually indeed it's the velocity of sound. Okay, so what you have seen is how the 1D wave equation is derived. I will write that again. So it's second derivative of partial derivative of pressure with respect to x, that equals 1 over c square, second partial derivative of pressure with respect to time. And that is my 1D pressure wave equation. Okay. And what this does is that it connects the second derivative of pressure with respect to its second time derivative. So it connects how pressure is changing in space to how pressure is changing in time. That is what it connects. And the thing which connects these two is this constant called C. Similarly, if we do the same process, if we follow a very similar process, what we did earlier, something very similar to that, then we can also develop a 1D velocity wave equation. And I will write that equation directly, and that is, so actually this is not V but U. So this is 1D velocity wave equation. Okay. So this very much similar to pressure. It connects rate of change or changes in velocity with respect to x, positional changes to their time related changes. And in both these equations, we have assumed that the flow is one dimensional, that is the changes in x and y are 0. Second assumption is the perturbations are extremely small in nature. Third assumption is that the material is, we have constant material particles flowing in the system. So these are some of the important assumptions. And the fourth assumption is that things are inviscid. So there is no heat generated because of viscosity. And there are no shear effects because of this. So this is for one dimensional flow, and specifically one dimensional for a Cartesian frame of reference. Now I just wanted you to at least have a look at a three-dimensional wave equation for pressure. So for 3 dimension, what happens is that it's pretty much very similar. So it is second derivative of pressure, and here pressure is not just a function of x and t, but it is a function of x, y and z and time. Then second derivative of pressure with respect to y square, and I am not going to write in parentheses x, y, z for sake of brevity, but if you have to be mathematically correct, then it has to be there. And this equals 1 over c square t square. So this is my 3D wave equation for Cartesian frames. Okay. And lastly, I will write another relation, and that is valid for spherical frame of references. So I will first write the equation. So here, instead of P, it is actually P times R over del R square equal to 1 over C square So this is 1D wave equation for spherically and this particular equation is valid if you have a point source of sound and it spreads in a spherically symmetric way. So as it spreads out, excuse me, I have to locate it at the center. As it spreads out, the progressive spreading out of these wave fronts is dictated by this particular equation. So that's all what I intended to cover for today's lecture, and we will continue this discussion tomorrow. Look forward to seeing you tomorrow. Thank you very much.